Okay. So next up is Yuhang Zhao, designing augmented reality systems to empower people with low vision.
Thank you, James. Hi, everyone. My name is Yuhang Zhao. I'm an assistant professor from the University of Wisconsin-Madison, and I lead the Medability Lab, where my students and I work on designing and building augmented and virtual reality technologies for people with disabilities. Actually, thanks to Brandon, who have mentioned some of the work on VR accessibility that we've been, working on, for example, controller and VR bubble. And if people are interested in, I'd be happy to talk more about them during the discussion. But today I'm going to focus on another important direction that my research has been looking at, which is how we design augmented reality systems to empower people with low vision. So low vision refers to visual impairments that cannot be corrected by contact lenses or glasses. There are many different low vision conditions. For example, if you see the slides, there could be blurry vision, central vision loss, blind spots, peripheral vision loss, and so on. And all of these different conditions have brought a lot of difficulties to people's daily life. However, different from people who are completely blind, low vision people, a lot of them, they still have residual functional vision, and they actually prefer, or they could be more efficient if they use their functional vision in many visual tasks. So in accessibility research, there has been all kinds of assistive technologies designed for people, more focused on people who are blind, that provide audio and haptic feedback to sort of compensate for the impaired vision channel. However, a lot of these work actually overlook the functional vision that low vision people may have, and their very unique needs that are different from people who are completely blind. And actually that is the focus of my research, is how we can design a system that can better leverage low vision people's functional vision and design systems to improve their visual ability in daily tasks. So talking about that, augmented reality glasses actually present us a very unique opportunity for to enhance low vision people's residual vision. And prior speakers have given very good definition of what AR is. And here I want to focus more on augmented reality glasses, which is a wearable device, so that people is, when they use it, is hands-free. And these glasses, they have different types of sensors, RGB camera, depth camera that can capture the surrounding environment and recognize the environment that low vision people may not perfectly see. And also it can render different immersive feedback, including both visual feedback, audio feedback, and some devices may support haptic feedback as well, to enhance people's ability in all kinds of daily tasks. And our research goal here is actually to seize this very unique opportunity and design, build, and also evaluate different AR systems that can provide direct visual augmentations for people with low vision to enhance their residual vision in various tasks. So to do that, I actually want to give two examples of our project to showcase how we do that, including a visual search task and also a wayfinding task. So I'll start with the visual search task. So visual search is a very common, basic, but actually very challenging task for people with low vision. So how we figured this out is we conducted an exploratory study with 11 low vision participants, and we observed how they complete a grocery shopping task. And during this process, we did notify that people have encountered all kinds of difficulties. But one of the most challenging tasks is actually to find this particular target from the very crowded grocery store shelf, right? And how they usually do is they have to get very close to the shelf, pick up each of the item one by one, bring them very close to their eyes, or use magnifiers to see the details. And if it's not a target, put it back and pick up another one, which is a linear process and very efficient. And what's unfortunate is there is just no very effective tools that can support this visual search task. So to address this problem, we want to leverage the AR glasses to further design visual cues to augment people's visual ability. So this system, we call it QC, which is a head-mounted display. So people can wear this display in front of their eyes, and we combine a camera with it to capture and recognize the surrounding environment, which we leverage some computer vision technology. And we design and render some visual cues to attract and orient the user's attention to the target so that a low vision person can simply follow, look at and follow these cues to reach a target more efficiently and quickly. And then the first question that we want to address is how we can design these visual cues, right? What visual cues would work more efficiently for people with low vision. So to do that, we collaborate with an optometrist to understand different low vision conditions. And we also look at different cognitive psychology theories to investigate what visual stimuli would work the best to attract people's attention. And combining these perspectives, we design 5 different visual cues that can potentially attract low vision people's attention, which are easier for them to see, but also not that obtrusive for them. So these are the 5 different visual cues, naming including guidelines, spotlight, meaning that we put the background grayscale, but only with the product with color. And also sun rays is like there are lines extending from the target to sort of expand the scope of that target, and the flash and movement. So one example actually zoomed in here is called flash, which is inspired by the cognitive psychology theory that onset, meaning the appearance of something that can attract people's attention even if it happens in the peripheral vision. And we sort of amplify this effect for people with low vision by generating this flash effect, which is sort of like a series, a continuous of onset that is happening so that it's easier for people to see. So with these different visual cues, we also allow low vision people to select and combine different designs based on their visual abilities to sort of customize and optimize their visual experience before they use the system. And based on the cue design, we start to build the system. So the hardware-wise, we combine Oculus Rift DK2 and with the webcam to capture the surrounding environment. And based on this hardware, we start to build the QC system. First of all, we incorporate a product detection component where we use a faster RCNN model, and we train the model based on a data set called RPC data set, which includes 200 different products and 30,000 images. And with our training, we reach a mean average precision of 0.85, which is a pretty good result from the computer vision perspective. But if anyone has run the deep learning model, and you may know that a lot of these models, they are actually not fast enough. They are not real time when you render that on an AR device. And to address that, we also incorporate an object tracking component based on our recognition. And by the end, we also have a speech recognition component to allow a low vision user to assign a target verbally to our system. So I want to show a video demonstrating how it works. So the user can just wear this headset, standing in front of the shelf, and then verbally assign a target to the system.
Look for pea snack.
And then she can scan around, wait until the cues show up, and follow the cues to read.
Look for onion rings.
And that's the example of another cue. All right, so that's how the system works. And to evaluate the system, we built a mock-up grocery store shelf with all kinds of different products. And we recruited 7 low vision participants who conduct several visual search tasks in front of the shelf. And they conduct these tasks in 2 conditions, including their best correction, meaning that they wear their correction lens, and versus QC with their preferred cues. So I actually want to use two video demos to demonstrate actually one of our low vision participants, how they experience the QC as opposed to one he's not using QC. So this is one he's not using QC.
Yeah. Start.
So this video is already speed up, but you can see how slow this process is. And he's actually very close to the shelf and look at each of them one by one.
Raisin, crackers, peanut butter. Sound good.
But with QC,
Ready?
Yes.
Start.
Sound good.
Good.
Man, I wish I had this when I used to work in a grocery store.
all right. So the video comparison shows the effectiveness of the system, and actually all of the participants really liked it. But I also want to show some numbers to demonstrate the effectiveness. So we look at the search time, and we find that QC had significantly reduced the participants' search time, which is almost to 1/3 of their original time. And QC also improved the people's search accuracy from 0.83 to 0.95. Unfortunately, it's not 100% because there could also be some recognition errors, but there is still improvement compared to their original performance. So QC was actually the first system that we built that can intelligently recognize the environment and generate more tailored visual augmentations for people with low vision. And compared with the more conventional low vision aids, for example, magnification that alter people's full field of view, our research tries to demonstrate the importance of more intelligently interpreting the surrounding environment and generate visual augmentations that is based on people's context. For example, the tasks they are working on, the environments, and also their different visual abilities. So that is QC. Of course, there are many other challenges that low vision people have faced in their daily life. So another example I want to talk about is a wayfinding task, which is also very difficult for people with low vision. But different from QC, where we purely focus on visual augmentations, in this project, we actually also want to involve audio feedback, because during our experiment and also conversations with a lot of low vision participants, we actually realized that even though they do want to use their functional vision, but audio feedback is also very helpful. A lot of them actually use audio-based tools. That's why in this research, we want to explore under the context of AR glasses and wayfinding tasks, what feedback modalities would be the most effective for people with low vision to navigate the environment in the indoor scenario, and also how potentially they may want to combine these different feedback to optimize their experience. So that's the general goal of this project, and how we want to do that is we leverage the sort of state-of-the-art AR glasses, which is the HoloLens, which has the spatial mapping capability that you can scan an indoor environment and anchor different augmentations in the environment. And we designed two different cues, including a visual cue, visual guidance, and audio guidance, so that we can design studies to sort of compare and ask people to customize their experience. So I want to talk a little bit more about how we design the cues. So they're all very standard, because this is sort of an experimental study to understand people's ability of using audio versus visual feedback. So the audio feedback, we leverage the very standard turn-by-turn instruction, which has been very commonly used by navigation technologies for people who are blind. And we provide 3 types of information, including the distance to the next decision point, and we update the information, report the information every 10 feet. And also the actions that people need to take at the decision point, for example, turn left, turn right, and also some information about the destination. And since this is an AR application, we want to leverage this immersive experience. That's why all our audio are spatialized, so that it sounds like that people are getting the audio feedback from, the next decision point. And our visual feedback is adapted from the very standard Google Maps interface to the AR glasses, including that we generate the virtual path, like this yellow path that people can just follow on to, navigate on this route. And also yellow star here that labels the position of the destination. And we design them in relatively bright color, relatively bigger size to enable low vision people to see them better. And we also try to, so all of these information is matched equivalently to the audio feedback. So we also generate, the actions the user need to take at the specific turns and also the distance to the next decision point. So how we display this is we actually provide two different ways in this case, based on people's different visual abilities. So one is the head attachment method, which is these, green icon, the arrows, and also the distance, that is the distance to the next turn and which direction the user need to turn. So this one is actually designed for people who with relatively limited field of view because it's head attached. So no matter where they look, this augmentation would follow them. And compared to that, we also have a more word anchored design, which is more like a street sign, so that we label, every 10 feet and also use that icon to label where, which direction the user can turn. Because the reason, actually we started with this anchored sign design because, which is more immersive, but the issue is it's very difficult for people with limited field of view to look. Sometimes they cannot really see the sign. That is fine. Okay. That is why we later design this floating window design that is easier for people with limited field of view so that they don't have to really look for them in the 3D space. So that's our design for the audio versus visual wayfinding guidance. And we, based on this design, we conducted a study with 16 low vision participants. So this is a floor plan of where our study was conducted. And we planned 8 different routes. There are very similar routes just for the randomization of the study. And each route is about 170 feet and with 4 turns. So in this environment, we actually want to compare users, the effectiveness of the visual versus audio feedback. So these are some measurements we are looking at. So beyond the basic performance of the navigation, for example, the wayfinding time and the error rates, like whether people have turned at the wrong places and so on. We actually also want to think more about the real world scenario where people do not only focusing on the navigation. There could be a lot of distractions. For example, you may want to pay attention to some landmarks, nice restaurant, you may want to talk to friends. That's why we also want to make sure our feedback is not that distracting. That's why we also look at the cognitive load of our feedback. And to measure cognitive load, we involve a secondary task, which is a vibration task, which wouldn't conflict with the audio and the visual feedback. So it's built on a smartwatch where the participant would wear, and it generates a series of vibration stimuli. And we designed 3 different vibration patterns and randomize them. So it's a randomized series of vibration stimuli. And the participants would feel this vibration and detect whether there are 2 continuous vibrations that are in the same pattern. If it is, and then they would need to tap on the smartwatch screen right away as soon as possible. And then we measure their performance by calculating the hit accuracy, which means the percentage of their correct hits among all the desired hits. So we use this to measure people's performance for the secondary task. So with this setup, participants worked in 4 different conditions: visual feedback with and without the distraction, the secondary task, and audio feedback with and without the distraction. And we asked them to try to follow the guidance and then arrive at the destination as quickly as possible. And sometimes it's very hard for them to complete both tasks at the same time. And in that case, we asked them to really prioritize the primary task, which is the navigation. So based on that, I want to show some representative results. So in terms of wayfinding time, so we actually do not see a significant difference between visual and audio feedback in terms of wayfinding time across all participants. But what's interesting is if we look at people with different visual conditions, for example, people with full field of view who don't have an impaired field of view, and then we see there is a significant difference. So actually for them, when they're using visual feedback, they navigate significantly faster when they're using audio feedback. So we try to actually talk to the participants and think about the reason. So here is the visual feedback we generate, right? And we figured that For people with full field of view, this is very effective because it gives people an overview so that they can better plan their step ahead. However, for people with limited field of view, what we'll see would be something like this. And then the visual feedback would be very difficult for them to perceive because it's very limited. We have heard a lot of our participants mention that they only see a bright rectangular shape in front of them, and they cannot really understand that is a virtual path. So that is the major reason that makes, there is no visual and audio, significance there for people with limited field of view. And at the same time, we find that in terms of cognitive load, visual feedback actually has a significant lower cognitive load for our participants because, when they hear the audio, when they hear the audio, actually it's ad hoc. That is why it's a lot more distracting. And one last slide here is we asked their preferences about how they want to combine the visual and audio feedback for different type of navigation information, including the overview of the route, what actions they need to take, their distance to the next turn, and also the destination information. So the yellow bars here represent the number of participants who wants to combine both of the feedback, and the blue represent people who only want to use the visual feedback. And the interesting thing is, even though for most information, people want to combine both feedback, but for the distance, most people only want, the visual feedback because distance is something that is very hard to estimate when they only hear an abstract number. All right, so that concludes this project. And what we learned from this is, even though visual feedback is sort of the winner, across all different perspectives, but people do want to combine audio feedback with it. And sometimes people use audio feedback to confirm their experience, and sometimes they even feel that they can see better when hearing the audio feedback. All right, so that's the two projects that I wanted to talk about. But those projects actually, from the AI perspective, they're still very preliminary because we focused on relatively simple tasks. But as the advances of deep learning technology, we actually may have the capability to enhance more complex and busy environment. For example, during the cooking process, right? If a low vision user wants to cut with a knife, instead of only recognizing the knife, right? We may also want to recognize where the handle is, where the blade is, so that we can better support them to not only see the object, but also better interact and use the tools more efficiently and safely. Okay, thank you so much.
Slide. I didn't know if you were starting.
Oh, no, it's fine. So, and yeah, just want to mention this work is currently partially supported by the McPherson Eye Research Institute from our university. Yeah, thank you.
Thank you very much. Are there any questions from the audience? Okay, I have a question. Have you thought about incorporating some sort of other feedback? If I'm getting navigation instructions, perhaps if I'm already wearing a headset that could do hand tracking, potentially the system could track my finger and it could be pointing in a certain direction. And the reason I bring this up is partly it comes to mind from Smith-Kettlewell. We have this old project called Talking Signs, whereby you can hold a receiver to get information, and by sweeping the receiver left and right, you can hone in on the correct direction that you want to go to approach the signal. So I was just wondering if something like that could be a natural mode that is non-visual, but very natural.
Yeah, definitely. I agree that I think what you mentioned is relatively more interactive, right? The user need to do something, but it definitely aligns with what they would usually do. For example, they're using a cane to sweep around the environment so that wherever they point to, they would hear, for example, audio feedback or the other feedback modalities. I definitely think that would be also a good direction to go that could be interpreted into AR systems.
There's a question back here. Actually, two questions. Steve and then Ben.
Got a very simple one. Is there an optimal AR headset in terms of price and functionality? Oh, that didn't work?
No,
Yeah, that's a great question. That's actually something we've always been thinking about, right? Because what would be the best platform or off-the-shelf devices we can leverage to support all of these applications? So far, I've used a lot of the HoloLens because it has a relatively stronger capability of interpreting the environment. It has the depth sensor and RGB sensor, but sometimes we also do feel the limitation as well, because sometimes the APIs have limitations and we don't really have the the depth stream from the camera. So sometimes we also consider like building up some little bit hardware device from scratch. For example, we use this is called video see-through. So instead of a optical see-through that you can look, there is a transparent display, you can see the real world environment. We can also use a VR headset, and then we can combine this together with some stereo cameras and the other sensors to better perceive the environment. So we actually tried both. It's hard to tell which one would be the best because it really depends on the applications that we are trying to work on.
I wanted to ask if a strategy for making an impact and getting these devices out to people would be to make a device that normally sighted people would also benefit. So I was thinking visual search. But I actually, I often have to spend a long time trying to find the particular cereal in the aisle. And if it were, I would use the device. And I know hearing aids have become popular among a certain group of young people because of all the added functionality they provide now.
Yeah, that's a really great point. I really love that because, many times people ask us, how, your technology to be generalizable, right? And that's actually a very great case that even though we design, assistive technologies for people with the visual impairments, but it can definitely benefit sighted people, for example. And actually, for example, the QC example, I did that work actually when I was at Cornell Tech, and we actually collaborated with Verizon and also build up a video smartphone-based application that for sighted people, they can also use that in a supermarket to find a specific product.
Okay, we have a few questions on Zoom, and just to say we're running up against a hard stop for lunch and lightning talk. So let me go to the Zoom questions, and there was also an earlier question for Ben, but first for Yuhang. I can find it. Oh, so from Dana, for future work, have you done preliminary assessments to learn what types of part or whole object information end users want? The knife is a great example, but I'm curious what the computer vision community can do to meet the model needs.
Yeah, so the question is what computer vision models we can use for the knife scenario. So this is actually on in the progress work that my lab is doing. And then we are considering some model examples, for example, affordance recognition, so that we can, based on the user's hand behaviors, and also you can also label a specific object by IDing the contours of the different components of the object, which is called affordance model. And we are thinking about those to further recognize the different components of the knife. But actually, that's a great question because we've tried a lot of the computer vision models, and we definitely encountered difficulties in terms of the recognition accuracy and potential delays, because a lot of models, it's really hard to run them with real time on AR devices. The best we can do for now, I think, is 10 frames per second. So we are actually collaborating with some computer vision experts to look into that too.
Dana has a follow-up. The question is more about a taxonomy for what data sets we need to build to support locating objects and their parts, what objects and then what nested parts are wanted.
So in terms of constructing the data set, yeah, that's a great question. So currently we are looking at more egocentric real-time video that people can capture, but we are also wondering whether there could be a major difference between the video captured by low vision people versus sighted people, because all the current data set, most of them are constructed by sighted people, as Dana has said in the prior session. So that's a very great question. So, but this is some very preliminary step we are taking, and how to construct the effective data set is definitely one important step.
Okay, thank you very much. And just one last question. This is going back to Ben's talk. I neglected to follow the chat. The question is, hello, how is the visual field test done by virtual reality? Would be authentic enough to provide disability certificates on par with HVF? Also, is it practiced anywhere now? If yes, where and how? If no, what is the way forward? I can show you the question if that's.
Yeah, okay. So the first part was, could it be used to document visual disability? Yeah, it seems to function very much like the Humphrey. So the real question is getting approval for that use, which is an expensive proposition because you have to do a clinical study that demonstrates efficacy. So there's no reason that it couldn't be. It seems to work more easily than the Humphrey and to be easier to take. And all the standard methods that you would use in the Humphrey to prevent malingering, which is when a person tries to pretend they have a disability that they don't have, can be applied and perhaps some more.
Okay.
And is it in use? It's currently being used by pharmaceutical companies in the exploratory phase. We've actually have some revenue from pharmaceutical companies for trials, and it's being used for research, but it is not. It's not being prescribed to patients yet.
Okay, thank you. So thanks to all of our speakers for this great session. Sorry we didn't have time for the general discussion, maybe during lunch, but let's thank all the speakers one more time.